Hey class, this is going to be a fairly short video, but enough to show you how to use Excel to create mathematical models. I realize, students in here have variation on how much Excel they know. Some people already know how to do modeling in Excel, and then I've realized some people don't. So just in case you don't, this is a really quick, easy way. Obviously, your text goes into the mathematics behind learning how to create a mathematical fit to data, but with technology now, there's so many faster ways of doing it, and also, in my opinion, beneficial ways of doing it, because if you're going to train students to how they would use mathematical models in real life, then they would certainly be using software. And so I think it's a good idea in this course for students to practice using the software. When I've taught mathematical modeling in my secondary classes, I've actually used Excel and some other programs. So kids are very adaptable to it. It makes it where the calculations are not so tedious. And while I believe in teaching them the mathematics behind it, I definitely cover that, but then I show them, once they know that, I show them how technology can very quickly and in a much less tedious way create the models for us. So I have created this hypothetical data set. While it may look similar to what you've seen on the benchmark project, it is not the same numbers. So make sure you realize that you'll actually have to go back from scratch, and what I'm getting ready to show you, you'll do it yourself because you'll have somewhat different numbers to deal with. The first thing we'll want to do is do a scatter plot. It's important to visually see what the data looks like because you can already sense what patterns would be reasonable fits and what models would be reasonable fits and what models would not be reasonable fits. So to do a scatter plot, I'm going to take my mouse and click and drag over both columns here. Whatever column is on the left, Excel will automatically put that on the x-axis. So if you ever needed it switched, you could just copy paste, or one way to do it is to just copy paste your columns in a different place where you put the one on the left that you want Excel to make your x-axis variable. So I click and drag, I come up here to insert, and then in charts in the middle here, I'm going to click on this, and the very one in the top left is the scatter plot. So I'll click on that. You see that we've got our scatter plot right here. It's easy in Excel to add labels and axis or titles and axis labels. All you would have to do is come over here and click the plus sign, check off axis titles, and then you could, notice it's given the little name axis title on both axes. So you could left click your mouse. I could type the word year, Y-E-A-R, press enter, and it puts that label. Similarly, I could come over here to the vertical axis, left click on that, put population, press enter on the keyboard, and if I wanted to change my title, I could do that. All I would do is come up here, left click, and then change that to whatever I needed. So population models or something like that. All right, but here's how you do the models and how you create them easily using Excel. You're in the benchmark assignment, you are going to be creating a linear model, a quadratic model, a polynomial model, and an exponential model, and then deciding which is the best fit. But what I would like to see is your work, your Excel work, where you've shown that you've actually created the equations for each of those four models, and you give the R-squared value for each of those four models. R-squared is an easy, real basic way of deciding which model is the best fit. There are other more formal ways of looking at model fitting that you don't really need to get into for the purposes of this assignment. So I'm going to be fine on just using the R-squared value to decide which model is the best fit. Excel will easily generate the R-squared value. And in my high school classes, when I've done mathematical modeling, we have used the R-squared as our way of judging the best fit. So if you wanted to look more into that, you could and just look it up online. But otherwise, it's a really simplistic way of evaluating the better fit mathematically. All right, so to get the trend lines, I am going to left click my mouse on top of the graph. I'm going to come over here to the plus sign, and I'm going to scroll down to trend line, and notice it already put a line, a linear model on top of the graph. So I'm going to come over here and click the arrow and go down to more options, and you'll see that by default, linear is always clicked. That's why it did a linear model. So since linear is one of the ones you're going to be doing, I'm going to leave that checked or clicked and come down here and click the box, the two bottom boxes, display equation on chart and display R-squared value. so that in your assignment, you would give this linear model and give the R squared value for that model. And then you would go on to create the other ones. I'm going to minimize that a little bit so that I can then show you how to quick and easily get the other models. So once again, I'm going to highlight, click Insert, Charts, Scatter Plot. I've got a whole nother plot of the same data. But this time, I'm going to come click the plus sign, go down to Trend Line, and I'm going to change this. So go down to More Options. I'm going to change this, and oops, that's not the screen I wanted. So let me go back and try it again. There it is. More Options should bring this up. All right, I'm going to change this now to quadratic, but notice we don't see the word quadratic here. But yet quadratic is really just a polynomial model of order 2, degree of 2. So I'm going to click this. It already says order 2. If you wanted to do a cubic fit or a quartic fit or whatever, you would just change this number anywhere from 2 to 6. So quadratic is order 2. Leave that. Click these bottom 2 boxes and minimize this so that now you see I have got, make this the same size, and click and drag, move that up. So I've actually got 2 out of the 4 already done. Now I have not gone back and evaluated and stuff, but I at least have the equations and the R squared values. Then you would do the polynomial. Now for the polynomial, since it did not specify what particular order, then here's what I'm gonna be fine with for polynomial. Highlight, insert, chart, scatter plot, move that down a little bit here. And for that one, yeah, I don't know, sometimes it works and sometimes it doesn't. All right, this is the screen we want. All right, so for polynomial model, I want you to just come down here and do the power model. So click on that and then click on the last 2 boxes and move that up. There's your power model. And y'all just realize 2e negative 38 is really like 2 times 10 to the negative 38th power, that scientific notation. So it's a power model because it's got like x to the, you can't read it. It's probably too small for y'all to read on the screen. But it's, I was trying to see if I could enlarge this a little bit. It's not letting me enlarge it. But once you do it yourself, you will be able to see it. Let me go make this bigger. Yeah, there you go. You will be able to see it. And you see that it's just x to a much stranger power than you normally would have thought of. Okay. And then it gives that R squared. And then lastly, so insert, chart in the middle. And I forgot to highlight, sorry, delete. Click and drag, insert, chart in the middle, scatter plot. I'm going to move this one over here. And then click the plus sign, trend line, more options. And again, I don't know why it's making me repeat this, but it is. Just be patient. More options. There's what I want. And then we've got to do exponential. So I'm going to come up here and click exponential. And then check off the 2 boxes on that one. And there's the exponential. Now this one, for some reason, left the line in there, which I don't want. So I'm going to click. I'm trying to click on this bottom graph, and it's not letting me. All right, I've clicked on the line. I'm going to delete that, and I only want it to show the exponential model here. Yeah, I don't know why it keeps showing that. It's got linear by default. That's why, but I just don't want it to do that. So let me see if it will let me click on exponential. There it goes. So yeah, before I go to more options, if I just click on exponential, it took the line out. I hope it's going to stay that way. And then more options is going to let me put the equation in the R squared. Yeah, it did okay there. So you may need to go ahead and click click on the model you want first before you then go down to more options. All right, so that's it. you get your 4 scatter plots done. Each one has a different model that is fit to it. And see, y'all, you know, if you had just eyeballed this ahead of time, you may have thought, oh, it's linear. But you really cannot eyeball real life data and think that you can just by eyeballing something tell the better fit. I mean, remember, we're not really expecting to see a perfect parabola or a perfect exponential curve. I mean, these are just pieces of models. And so realistically, if I look at all my R squared values, the quadratic is actually the higher R squared that's closest to 1. And so that's going to be the better fit. And you even look at the graph and see that, yes, the quadratic model is actually coming closer to fitting these points. You always expect it, or I should say, you rarely would ever expect to see a perfect fit where every point is on the model itself. That would be very unrealistic. But you hope to find the distance between the points and the model to be minimized. So, you know, when I'm looking at these 4 models, the quadratic does appear to have the points overall closer to the model. And that shows up, that's justified because it's got the higher R squared value closer to 1. So, you know, that would be the one I would pick. And, but then if you wanted to then, you know, part of the exercise is to use the model that you create to actually make the predictions with that model and see what the deviation is from the actual population. Like, for example, the linear model up here. If I wanted to come over here and see what the projections were from that model, like I'm going to type linear up here, then here's what I could do. I could take that equation and I'm going to start right here with an equal sign, and then I'm looking over at the linear equation, 0.3666 times x. So 0.3666 times, times, you need to put the asterisk in for times. And then the x is the population year. Not the population, the x is the year. Remember, that was the independent variable that Excel chose and that I wanted Excel to choose as the x. So instead of an x, notice the first year is in cell A2. So I'm going to type in capital A2. It highlights the year 1900. And then back to my equation, minus 650.36. So minus 650.36. Press enter. And what the 46.18 is the population that my linear model would predict in the year 1900. Well, the actual population was 41.3. So my model is overestimating the population in 1900. But in some of the other years, you can see that the graph is under the actual observations. So in some years, it's going to underestimate. To get the other year projections, I just click my mouse in this first top box that I just got, come over here to where I have a nice little black arrow in the bottom right, and I click and drag my mouse, and what Excel automatically does is inputs these other years, 1910, 1920, and so forth. So here are all the projections. You can see that most of these are very close to what the actual figures are, but if you get the difference, take your population minus the your actual population observed minus the predicted, that's how you get residuals. So like the residual in 1900 would be 41.3 minus 46.18, and you would get your residuals. This is how you're going to be able to add in the years like 2000 and 2010, and your model is predicting those. Okay. You'll have to go get these other actual observed populations from the website that was provided for you. And then you can just calculate the residual yourself. Whatever the actual population was in 2000 minus the prediction will give you that residual, and similarly for 2010. So I'm just trying to illustrate how easy Excel will make that. There is something to be very careful about though. While the linear model projections look pretty close, if we took the quadratic model and used these numbers, you would see that the projections are not very close to what it looks like. For example, I'll come over here to quadratic, press enter, and I'm going to put in this equation just to show you, just to go ahead and show you how off it really is and to give you a way to fix that. Okay, hang on just a second. All right, so if I came over here to get this equation, I see, well, first we have to start with an equal sign. I see negative 0.003 times, and I see the x. Well, remember the x is A2. So A2, but that is squared. So I'm going to do squared. Notice how that's done in Excel. Plus 11.992. I'm just looking over at the equation times x. So times A2 minus 11954. And then I press enter. Well, there's a problem. When you look and see the projection, it says 0.8, but yet that's not what is shown on this graph. I mean, in fact, the projection from the model looks almost identical to the actual population. So why is it giving us incorrect projections from the model equation that was given to us? That is because of rounding issues. And, you know, when you start having exponents involved, and y'all know this as math people, if you round a little bit when exponents are involved, by the time you finish, you're way off. That's what's happening here. So what you're going to need to be careful about is making sure your models go to more decimal places than just like three places, which these go to. So I'm going to actually delete this up here. And what I'm going to do is come over here and click on this model. And if it doesn't already show up, like it's already shown up because I've been playing around with this, but otherwise, you're going to right click on top of the equation and go down to Format Trendline Label. And when you click on that, this will show up. What I want to do is go down to Number Category and click the drop down, go to Number, and change the decimal places to like, even at a minimum, I know it's going to look tedious, but at a minimum, change it to like 10 decimal places and then click enter on the keyboard. So that now what it's done is given my model, let me slide this where you can see it, given my model to 10 decimal places. And so instead of negative 0.003, you've got it shown as negative 0.0029, blah, 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 blah. Definitely something that would round to negative 0.003. But let me just show you the difference. So I'm going to come over here back to my quadratic first box, type in an equal sign. Now I'm going to put in this long number that I see, 0.0029. This is the tedious part, 886,364 times A2 squared plus, and I'm just copying the equation I see, 11.992, 401, 5152 times A2, which is the times X part, minus 11,953.979, 242, 4245. Press enter, and now look at the population projection. It's much different than our earlier 0.8, and look how close it is to the actual population. Click and drag, and you're going to find that all of these now are very close to the actual populations, and that's because this is such a good, strong fit with this model. So you're just going to have to, whichever model you pick, and you're trying to calculate those residuals I mentioned, you're just going to have to stretch this out to more decimal places. Otherwise, you're going to get some really weird projection and think, what am I doing wrong? Well, you're not doing anything wrong. It just needs to be stretched to more decimal places. So that's it. And, you know, you can use the same procedure if you needed to on these other models, if those are your better fits. Hopefully, in other words, now you've gotten the hang of it. You can, in your assignment submission, include these 4 plots with each of the 4 models and each of the R-squared values, and then just mathematically use what I've shown over here on the left to calculate your residuals, or you can use a calculator. Just make sure you show the projections that you've gotten and show the residuals, the differences between your actual population and your projected population. So that is pretty much it. It's a really nice tool to use for modeling, and easy enough that high school kids usually can pick up on this stuff, pretty quickly. So I hope that that's helpful for y'all.